Hello health champions! Isn't it funny how some people say that you have to eat sugar and carbohydrate in order to generate blood sugar for your brain? And yet there are a lot of people who eat zero carbohydrate in their diet and their blood sugar is too high. Where does that blood sugar come from? Well, if you're not eating it, it means that your body is making it from something else. Now the questions we want to answer are: how does the body make sugar from other things? Where does it come from? What type of foods? And why does it matter? Even though most people change the way they're eating, change their lifestyle or their diet because they want to change their weight, they want to lose weight for the most part, there is more to it because the same mechanisms that drive weight up are also associated with type 2 diabetes, insulin resistance, and disease. And the things we're trying to change are blood sugar and insulin. We're trying to lower blood sugar, lower insulin. And you can find both of these markers on your blood test. But in order to change the blood test till next time, you want to understand what sort of foods are increasing those so that you can reduce those foods. So to help with that, they have created something called the glycemic index and the insulin index. Now the glycemic index is virtually useless because they've only created these values in glycemic index for things that contain carbohydrate. Carbohydrates are not the only thing that can drive up blood sugar and insulin. The other reason it's useless is that they've only tested high glycemic foods, such as carbohydrates. So they set a value for glucose, which has zero fat, zero protein, and 100% of calories, 100% of the weight is carbohydrate, and therefore it has a very high glycemic index and a very high insulin index. But then they compare that to foods that have slightly less glycemic index. So bread is in the 70s, but that's still an extremely high glycemic index. And that's why we don't want to pay too much attention to glycemic index, because what they call low isn't really low. Problem with the insulin index is that the data is almost non-existent. The idea of the insulin index is very, very good because insulin is really what we're looking for, but there's so little data to go by. So in this video, we're going to talk about the mechanisms so that we understand and we can look past the numbers, because you don't want to really look in tables after insulin index, because when they test it, people react differently and some of those numbers are quite questionable. So if we look at skim milk, that's a product where they have removed the fat. It has all the original protein and carbohydrate. So carbohydrates are dominating in skim milk, and therefore the glycemic index is pretty close to that of glucose. It's not real close, but it's fairly high. The insulin index is much, much lower because the carbohydrates in milk is called lactose, which is broken down much, much slower. So some of this insulin index comes from carbohydrate, which is broken down slowly, and from protein, which is broken down even slower. When we look at whole milk, it has more fat, so it's going to have most of the calories from fat. Now we get a glycemic index that's much lower, but we get a somewhat lower insulin index because a lot of the protein is still there, but the fat is slowing it down. And when we look at full fat cream at 37%, then the vast majority, way over 90% of calories are from fat. So the glycemic index is often quoted as 0, which it isn't strictly, but it's really close to 0, and the insulin index is very, very low. So the lesson is that carbohydrates drive it the most, both glycemic and insulin. Protein can drive it somewhat, and fat slows it down. But what about these people on zero carb diets that still have high blood sugar? That is because of gluconeogenesis. The body is making glucose from something else. And oftentimes they say that glycogen contributes to gluconeogenesis. And it sort of does, but not really in my mind, because glycogen is already glucose. You're not making it from scratch, and you're going to run out of glycogen pretty quickly. And then your body has to make it from something else. And your fat is bundled with something called glycerin that your body can make carbohydrates, make glucose from. And you can also make it from protein. Protein is made of little building blocks called amino acids, and they can be converted into glucose as well. And this is where I want to focus mostly today, to really understand how different types of protein are converted differently. They have different impact on glucose and insulin. The main purpose of protein is to become tissue. Ideally, that is why we eat protein. We want to turn it into body parts. And if we're successful, then we get muscles and bones and hair and skin and so forth. And they're primarily made up of protein. Now, the protein that doesn't turn into tissue, the excess, or the things that don't fit, the things we can't match and use for tissue, they become fuel. So the question is, which different proteins turn in more into tissue or more into fuel? Insulin's role in the body is storage, or anabolism, means building up. Insulin can build up fat tissues and muscle tissues. Insulin assists glucose into the cell, and this glucose gets converted to glycogen and stored, which we can only store a little bit, and then the rest gets turned into fat. But the same thing happens with amino acids. That amino acids also gets assisted into the cell by insulin, and then they get stored as protein, primarily as muscle. Now, we have to understand that this portion, the amino acids portion of stimulating insulin, its role in stimulating insulin is minuscule. It is so small that we can disregard it in our discussion here. The reason insulin gets triggered is by blood sugar. Now we need to understand a little bit about protein. So you eat food, it has protein, but your body has to break down the protein into amino acids. So if you look at this picture, these individual little components, these are molecules called amino acids, and then we string these together by the dozens, by the hundreds, by the thousands, and then they form proteins. And because of how these proteins have different charges, then these proteins fold themselves and create different shapes, and that is what's unique about protein. So we have to break these individual pieces down because these can only pass across the intestinal membrane. They can only be absorbed one by one. If we don't break them down, we can't absorb them. And then once we've absorbed them, we are putting them back into other proteins that have specific purposes in the body. Even though there are hundreds or even thousands of amino acids, there are 20 that are used in the human body to configure these proteins. And out of these 20, there are 8 or 9, depending on who you talk to, that are essential, meaning that we have to add them in the diet. We have to eat them because the body can't make them. But if we eat these 8 or 9, then we can make the other for a total of 20. And the reason they don't know quite sure if it's 8 or 9 is that it seems histidine, which is the 9th one, can be made from the other 8. But today we'll just assume that there's 9 of them. We often hear about animal protein versus plant protein in terms of the protein being complete or not. And we also want to talk about how much, what percentage of the protein is being utilized. Does it turn into tissue, meaning it's utilized, or does it turn into glucose and fuel and drive insulin? And now we want to think of these 9 essential amino acids as building blocks or letters. So if you're going to spell out a 9-letter words, you need 9 different letters in this case, 9 essential amino acids. So this is a protein called prolamine. It has 9 letters, 9 different ones. But let's say that you're missing 1 letter. You have 8 letters, you don't have the 9th one. And now you go to spell a 9-letter word. You're going to build a protein with 9 essential amino acids. How many of those words, how many of those amino acids can you build? And the answer is 0. You cannot spell this word unless you have that letter. And what this means then is all of the other amino acids gets turned into glucose. And that means this protein is not complete. And that's why it's so important to eat a variety of foods, especially if you are a vegan or vegetarian. But it doesn't stop there. We also have to understand utilization. And this depends on if these amino acids occur in the right ratios. So let's say that we have 2 of this amino acids and 4 of this and 3 of the O's and 6 of the L's and so on. And now we go to spell as many words as we can, as many 9-letter words. We're trying to make this particular word. How many can we make? Well, obviously, the lowest denominator, the 2, we have 2 A's and 2 P's, so we can spell the word 2 times. And all of the other amino acids are going to be converted into glucose because they get left over. For this particular word, we can only use the combination of these amino acids twice. They may be used for some other proteins down the road, but for this particular case, most of it, this amount, gets converted into glucose. And here is how they measure this stuff. It's called protein utilization. So it's very, very simple. Protein has something called nitrogen in it that doesn't occur in fat or carbohydrates. So you ingest a certain amount of protein, 100% of what you ingest, and then they measure how much of this nitrogen is excreted. They know how much nitrogen you ate, and then they measure how much went out in the urine, and the conclusion is whatever stayed in the body is being utilized as building blocks, becomes tissue. And like we said, that's the purpose, is to become tissue, so that's the utilized portion. One of the best foods in terms of utilization is a whole egg. Almost half, 48% of the protein gets utilized, 52% become excreted. When we look at animal meat products like meat, fish, poultry, pork, virtually any animal protein, they're going to be very, very close, right around 32%, right about 1/3. And then when we look at whey, soy, and plant proteins, they are only 17% absorbed, only about 1/6. Whey is a dairy protein, but it's processed. It's only a portion of the protein in dairy. Soy is often quoted as the most complete plant protein. That some say that it's better than animal products, but because of these amino acid ratios, it's only used 17% of it. And the same goes for virtually any protein powder, whether it's hemp or pea protein or rice protein, only a fraction gets used and becomes tissue. The rest of it becomes glucose and will drive insulin. So the only other issue I want to talk about is overeating, because that is also a huge factor. Even if you eat something that's supposed to be highly utilized, but you eat way, way, way more than the body can use, there's only so much protein that fits into your body's amino acid pool that can circulate in the blood. And once you go beyond that, then any excess will be turned into glucose and fuel and be burned, because your body can only use so much at a time. But now it gets really, really interesting. Now let's start understanding some of these principles. We said a whole egg is one of the best ones. It gets used at about 48%. But here's the kicker. Egg white only gets used about 17%. Why is that? Because when we look at their composition and we start understanding how the body uses this, egg white is virtually all protein. And it has a very high glycemic index of 55. What most people don't realize is egg yolk actually has more protein than egg white. People throw away the egg yolk and they think, oh, egg white, that's the good, that's the protein stuff. But it turns out the egg yolk has more protein, but it doesn't stop there. The egg yolk has the pieces, the amino acids that are missing in the egg white, and that is why the egg white is only partially used, but the whole egg is used to a much, much higher degree, and therefore the insulin index is 21 versus 55. The utilization is 48 versus 17. So 83% of the egg white gets turned into glucose, and that's why it drives so much insulin. Now let's look at a few other foods. And remember I said that there's so little data on this. They started looking at this in 1997, and there's only been a handful of studies, and they're very incomplete. So there's a lot of discrepancy in the numbers. Beef has been quoted all the way from 15 to 51 on the insulin index, and fish has been quoted all the way from 12 to 59. And we can't really find out what type of beef or what type of fish. They won't tell us how much fat was in there. So it seems very unlikely if something has 0 carbs and similar protein that they would vary this much. And then we look at another list and we see cod comes in at 12. We see chicken is at 17, hot dog at 16, bologna 11, and bacon 9. So these numbers are all very consistently low, and we see that they have 0 or low carbs. They have similar amount of proteins, except the processed hot dog and bologna, which has less because it has other stuff in it. So basically we see that they're relatively consistent, low numbers, and the proteins are similar, and the fat slows it down. And nowhere could I find any numbers on ground beef. None at all. So I try to estimate some numbers based on our understanding now. We know that most animal products, fish, beef, chicken, they all seem to be utilized at about 30%. So that means 70% gets converted to glucose. We also know that fat slows it down. So we look at something like chicken at one end of the scale, and we look at bacon on the other. They have similar amounts of protein, but the fat slows it down. Now, if we look at something like 30% fat ground beef, then the ratios of fat and protein are similar to the bacon. The only difference really is the ground beef has a little more moisture to it. So the numbers, the insulin index, should be very, very similar. So I just said in my estimate here, in my opinion, I think that number would be somewhere between 8 and 12. If we look at 20% fat in the ground beef, that should be a little bit higher because there's less fat to slow it down, and there's a little bit more protein by percentage, so maybe 10 to 15. If we look at ground beef with 15% fat, it's a little bit higher, and if we look at lean ground beef, we might get up to about 15-20, which would be similar to the range of chicken. If you enjoyed this video, then that would be a great one next if you want to understand more about how the body works and how to truly master health. Thank you so much for watching.